Welcome to this second session of the Barcelona Mathematics and Machine Learning Colloquium Series. This is an activity organized by the University Autónoma of Barcelona with the aim of gathering together here all the Barcelona research centers and universities, and also of sharing this with the global community and all the people who are interested from abroad. So let me give a special welcome for the people who welcome us from different institutions. Let me just remind what this activity is about. We just want to focus on two simple but interesting questions. What are the mathematics behind machine learning, and what can machine learning do for mathematicians in a very broad sense? We'll do that 3 times a year. We'll do it online, and you can find all the information on our website. How we will do it? So we'll have a talk, and then, equally important, some discussion. Still, questions are welcome anytime. So if you have questions during the talk, you can use the chat, you can raise your hand, and you can also use the question and answer option to post anonymously if you wish. And the most important bit of this activity is the who. And let me remind you the 3 speakers we have this year. And today we welcome Liz Munch. Liz did her PhD already on topological data analysis in 2013 at Duke University. And today she is an associate professor at Michigan State University, where she works on applied topology and topological data analysis. And today she'll tell us about crafting topological features for machine learning pipelines. So Liz, thanks a lot for accepting this invitation, and the floor is yours.
Thank you. Okay, I'm gonna figure out screen sharing first. Oh, hold on. Now I lost all my screen sharing buttons. Share. All right. See if that'll work. Okay, can you see that okay?
Yes.
Fabulous. All right, well, first off, thank you all so much for the invitation. It's always very nice to be able to talk to people about the stuff we've been doing. And it's lovely to see so many people online and interested. Feel free. I'm going to kind of talk about a bunch of different vaguely related topics. And so if you have a question, feel free to stop me and ask a question, because we're going to kind of go a little all over the place. So what I wanted to talk about was, I guess, less of the machine learning side of things, but sort of the how do you get some of your encoding and things you want to measure into a space where you can actually put it into a machine learning pipeline. So the work that I do is largely focused on encoding and quantifying shape in data. And so it kind of depends on what I'm doing for the day, whether or not it's sort of obvious versions of shape. So we do a lot of things in my group related to plant biology. So for instance, these are X-ray CT scans of walnuts. So you're actually seeing the outside of the walnut, and you can kind of see the inside meat and all of the sort of interesting structures that go on the inside. We do things with a lot of X-ray CT scans of plants. So these are down here. This is a pepper. This is some form of citrus. We've done things in my group related to stuff like scanning. They actually call these tree cookies. So you take a slice of a tree and you can do things related to measuring, how old it is and looking at the different patterns and structures inside. We're actually going to also talk today about sort of different weirder ways of measuring shape where shape is less obvious. So for instance, you can measure time series and look at different sorts of time series and try to encode those in some sort of structure where you can measure the shape with the hope of understanding something about the original time series. So a lot of the goal of what we do is try to encode something about shape and structure in something quantifiable, largely with the plan of passing it to machine learning algorithms. So a lot of my work tends to fall into the following pipeline. We have some sort of input data, right? So scans of plants, time series, we've done things with proteins, anything where you have sort of a lot of data points that you're trying to understand something about shape and structure. We turn this into something that I like to call a topological signature. So we'll talk about some examples of these throughout the talk, but the idea is that it's some sort of representation of the underlying structure of the data that I can, first off, make my computer, spit out for me, but then also that I can use as some representation of an aspect of the original input data point. And so in this case, this is often what you might think of as like a lossy procedure, just because it is not going to be a complete picture of your original input data. But the goal is that if you've sort of set these things up in a way that they measure something that might hopefully be useful, that they are encoding enough of the interesting structure that we can use them for later. So once you do that, the hard part with these is that these structures that we use to encode information about the shape are often not immediately presentable to machine learning algorithms. So usually they're not things like vectors or a list of points or something like that. We have to work a little bit harder to take our topological signatures and turn them into something that we can actually use for machine learning analysis that still preserves the underlying mathematical constructions that we use to build them in the first place. So for a lot of today, we're going to talk about some examples of topological signatures that we can use, and at least some basic ideas of how you can turn them into something that you can actually pass to machine learning algorithms. All right, so this is sort of the way I tend to view all of this stuff, that our general goal in TDA, topological data analysis, is provide some sort of summary of the shape of data with sort of the following, general life goals. So quantifiable, meaning I should have some computer algorithm that can actually make this spit out for me. Concise, so it should be smaller than your original input data. Comparable, so that gets really interesting related to trying to come up with metrics and ways to compare these objects. And then with respect to those metrics, we want this to be robust. So the world never hands you a perfect input data point. It hands you a noisy version of whatever the ground truth is. And so any representation we have should be very close to what the ground truth true answer would be, even though I don't have access to it. So for the purposes of today, we're going to look at least one class of topological signatures. So I like to think of a lot of the tools that come out of TDA. This is by no means a full list. But a lot of the tools that come out of TDA can be sort of split up into two piles. So there are the algebraic sorts of objects, and that's what we're going to mostly discuss today. These are things like persistence diagrams or barcodes, if you've seen those show up in places. We're going to do a lot of stuff with Euler characteristic curves in this discussion. But there's also a family of more graph-based representations. Things like merge trees, mapper graphs, Reeb graphs, a lot of graph-based structure, underlying structure of your input data. There's a lot of really interesting things to do with that in terms of trying to get those things into some sort of machine learning applicable algorithm. But for the purposes of today, I'm going to focus on two applications where we use the algebraic signatures instead. All right. And so in general, the whole idea here is that I want to come up with some sort of topological signature, and I want to encode something useful about the data. And I also want to find a way to pass this signature to your machine learning or deep learning pipeline in a way that respects the topological information. There's a lot of sort of ignoring a lot of the structure. You can just kind of hand things to machine learning, but then you're kind of losing a lot of the work you did in the first place. So that's going to be our general goal. All right, and so for the purposes of this talk, we're going to talk about two different projects that are going to look kind of different, but are using sort of similar, maybe not similar, related tools. I'm going to talk about one project that we did that involves encoding shape and structure in Barley. This involves a lot of 3D X-ray CT scans. And then I'm going to talk about another family of projects that we've worked on that are related to a representation of time series data into some sort of structure that you can measure with things like persistent homology. Okay, and just in case you're coming in late, I want to please feel free to unmute yourself or ask questions. I'm happy to take questions as we go. All right, so let's talk about Barley. So this is one of my favorite projects just because compared to a lot of the other stuff that we do, the setup for the topological signature is probably the simplest to explain. So even if you are not a mathematician, haven't seen any of this background, this is sort of a really nice, very simple way of representing your data. All right, so Euler characteristic. So it turns out that if you look at various shapes and structures, one thing that you can do is you can start breaking them up into pieces. And the first way to break things like 3D objects into pieces is to look at things like vertices, edges, and faces. So in my tetrahedron example here, I have 4 different vertices, 6 different edges, and 4 different faces for the 4 triangles that you can find on the other sides. So it turns out that if you take alternating sums of these counts of vertices, edges, and faces, you get something called the Euler characteristic. So what's nice is the Euler characteristic is just a number. So I handed you a space, and you handed me a number. And if you hand me a lot of the standard Platonic solids, all of the standard Platonic solids, if I take this alternating sum, what Euler noticed in the, oh, I should know this, 18-ish hundreds. So what he noticed was that if you take this alternating sum, you always get 2. So my tetrahedron, 4 minus 6 plus 4 is 2, cube is 8 minus 12 plus 6 is 2, etc. So it turns out that this is a first example of a topological invariant. So the idea is that if you hand me any of this, or a shape that represents the same underlying topological space, the Euler characteristic will always be the same. So in the case of the examples I had on the previous slide, I had a tetrahedron, I had a cube, I had a whatever we had, what do we have down there, octahedron. They're all sort of topologically the same as a sphere. So the sort of idea to keep in your head is that if those things were made of nice, stretchy, putty something, I could kind of squash all of them and still get something that looks like a sphere. And by sphere, I mean outside boundary of a ball with air inside. And so even though they've got points and bends in different places, they're all basically topologically a sphere. So in this particular case, the Euler characteristic of anything that looks like a sphere is going to be 2. That's what we saw on the previous page. If you hand me the Euler characteristic of anything that looks like a torus or the skin of a donut over here, you're going to end up with a Euler characteristic of 0. It doesn't matter how you break this thing up into vertices, edges, faces. This alternating sum will always give you 0. So what's really useful for this is, okay, so first off, I know that if you hand me 2 spaces, I don't know, under a blanket or something, and you can't see them, I'm looking at these 2 different spaces, and then I ask the question, okay, all you're going to tell me is you're going to tell me what the Euler characteristic is. If you tell me that the 2 spaces have a different Euler characteristic, the one thing I can definitely promise you is that those 2 were different spaces underneath that blanket, right? So if one of them had an Euler characteristic of 2 and the other one had an Euler characteristic of 0, I can promise you at the very least that those are not the same. Now, one thing that I cannot do is I can't tell you if you told me both things under the blanket had Euler characteristic 0, I can't promise you that they were the same thing. So for this particular example with my little table here, the circle, the torus, and the Klein bottle all have Euler characteristic 0. And so I have absolutely no way of deciding which one of those options it is. But in terms of measuring stuff, this is actually a very nice way of taking something about shape and structure and turning it into a quantifiable representation, right? I take a shape, I give you a number. Excuse me. So here's how we're going to use this in data. Oh, are you not connecting? There we go. It's back. Okay. Here's how we're going to use this in data. So a lot of the data I'm going to use for this part of the talk is going to be something that probably came from either a 2D or 3D scans. So we're going to do a lot of examples on 2D because the pictures are easier, and then we're going to do a lot of the actual application on 3D because life is 3D. So what we're going to do is we're going to take our 2D scan, and we're going to turn this into some sort of binarized image. So right now, all I'm doing is some sort of simple thresholding where I'm just going to decide whether or not a pixel is included in the part of the image I like or not. So for the example of this particular fern leaf, I'm looking at all of the white pixels, which make up, all these different pieces. And so I am just going to encode all of the information related to the white portion of this particular picture. So I can do exactly the same thing I did on the previous slide, where now I count how many vertices, edges, and faces I have, where, again, now I'm kind of working with this in some sort of, I've got vertices at the intersection of all my pixels. I've got pixels that are included and some that aren't included, etc. But what I'm going to do is I'm going to keep the white region of the picture and get an alternating sum of these things. that gives me an Euler characteristic. And so in this case, the Euler characteristic of this particular picture is something like -200, plus or minus. Right. Now, this is not particularly useful, right? I handed you, here's a leaf. It's got a Euler characteristic -200. That's great. What do I do with this? So what we're going to do is, rather than representing our data as this single number, which is just not quite useful or discriminative enough to really do anything about it, what we're going to do is we're going to pass to this other related idea, which is called the directional transform. All right, so here's the idea. This is actually a picture, the same underlying data set. I've got the same fern leaf piece. I'm just going to color it a little bit differently. So what I can do is I can take the portion of my image that gives me this fern leaf. What I'm going to do is I'm going to pick a direction. So in this particular case, I happen to have chosen this, hoping that shows up, this blue direction that's going that way. And what I'm going to do is I'm going to define a function that's just increasing in that direction. So the level sets are perpendicular to whatever thing I just drew, assuming I can actually draw straight lines. And I am generally increasing going in this direction. I'm a topologist. I don't really care exactly what the numbers are. I mostly just care about the directionality. All right. So what I'm going to do is I'm going to break this thing up into pieces based on this function. Excuse me. All right. So, let me do that on this page first. Okay, so what we're going to do is pick a threshold. So let's pick a threshold of a color I can find. So somewhere around, oh, nope, come here. Is that going to show up? All right, so let's pick a threshold of approximately 20, assuming I can find my colors. What I can do is I can look at all of the pixels that have function value less than, let's pretend that's approximately 20. So I want all of the pixels that are this way, all right? What I can do is I can stop at that particular level and figure out the Euler characteristic of that. All right, so I can come up with the Euler characteristic there. I don't know, maybe it's something like, I'm making numbers up, but let's say it's, I don't know, -100, right? Then what I can do is I can increase my function value. So I'm going to look somewhere around maybe 25. If I increase my function value, I can look at all the pixels that are less than this. Now, that includes all the ones I had before, and I've got a little bit more than that. And I can figure out the Euler characteristic again. So I now have my Euler characteristic, which is now something like, I don't know, -150. Again, I am making up numbers. All right. What we can do is we can threshold at a bunch of different locations and see what the Euler characteristic is at every stopping point I picked. And what I'm going to do is I'm going to mess around with that with that threshold, increase it going in, well, right now this way, and keep track of the Euler characteristic. So here's what I have. So here's one example. Let's see which one of these is my, none of these are the same as before. The idea is that for any direction that I picked, I can get this function. So let's look at a couple examples. So in this particular one, this first one is increasing in this direction. Again, I'm going to pick a bunch of stopping points and figure out what my Euler characteristic is. And that gets me this function value down here, right? So my function here is just the Euler characteristic at a bunch of these stopping places as you increase. Okay, this is sort of a bad picture just because I should restart the axes every time. But what I can do is I can pick a different direction, and I can get the Euler characteristic again in that direction. So for this next picture, I have increasing function value going this way. I'm doing the same sort of thing where I'm going to threshold at a bunch of different locations going this way. I'm going to stop and figure out my Euler characteristic, and I'm going to keep track of that as a vector or a function. So what we end up having is for any direction, in this case on the circle, for any way that I can sort of point my arrow, I can get this function defined on for every real value I get an integer, because Euler characteristics are always integers. So what we do is we stack all that up together and try to see what's going on. So in this particular example, again, I am living in, my data started as a picture in the plane. Every direction I can go in the plane is a circle, which topologists will call S1, just because it's a one-dimensional-ish looking manifold. For every direction in S1, I get one of these little functions. I'm going to just discretize this so I have a vector, and I can stack all these things up into an image. So in this case, if I pick a direction, I get one of these vectors going this way for different thresholds from that Euler characteristic transform. And the bottom down here is a circle. So you can either look at it as this image on the left, or you can look at it as this wrapped up cylinder thing. But the idea is that this thing is now something that machine learning is very happy with dealing with in terms of passing in data, right? This is now some sort of matrix looking thing, vectors of numbers. This is very easy to just hand to your favorite machine learning algorithm, which is what we did. So let me talk about the application a bit. Oh, wait, let me talk about why this is okay first, and then we'll talk about the application. So the reason this is okay, well, better than okay, the reason this is even better than working with the Euler characteristic by itself is this actually is a complete description of your original input data for certain types of nice input data. All right, what do I mean by that? So when we started talking about the Euler characteristic, we talked about the fact that I can have two different spaces that have the same Euler characteristic, and so I can't distinguish them using just Euler characteristic by itself. However, if my input data is, well, simplicial complex is embedded in R3, so basically just nice enough data sitting in R3, this construction is actually injective. So what does that mean? That means if you started with two different unknown complexes, spaces, whatever things you wanted to ask questions about, if you spit out this data cylinder sort of looking thing, if those data cylinders are different, I can promise you the original spaces were different. So this is a complete description of what's going on. And so furthermore, you can just hand this to your favorite machine learning stuff. So let me talk about the application where we actually used this guy most recently. All right, so I have some lovely collaborators who work in plant biology, studying plant morphology, so shape and structure in plants. So we got access to this really cool data set. So this data set, so starting in the 1920s, Harry Harlan and Mary Martini, who are the folks hanging out up here in the top right, so they traveled around the world and collected examples of barley from lots of different places. So here's where all the different founding strains come from. So they traveled all over the world. They picked up all these different examples of barley, brought it back to California, and put them out in a field. And so what they did was they, and I apologize to biologists in the room because hopefully I'm not going to mess this up, but what they did was they took all pairs of the founding lines, crossed them with each other, and then took the resulting seeds and planted them out in a field. And then what they did was they took the resulting seeds from that, particular line when they grew it out, collected all the seeds, and did it again. And so this is an artificial evolution experiment, and they did this for something like 50 years, right? So this has, the results of this experiment, they've stored examples of all the barley panicles and the seeds and all sorts of, it's just got a ton of data. And so it's gone through a bunch of different people who have maintained it, most recently being my collaborator, Dan Koenig, who is currently there maintaining this particular data set. So he took examples of these founding barley panicles and some from some of the other later generations and shipped them to us in Michigan. And my collaborator, Dan Chitwood, put them into his X-ray CT scanner. So the X-ray CT scan, once it comes out, so this is a very cleaned up version. So our barley panicles kind of start looking like something like this. Turns out those stringy things are very hard for scanners to find. The result is something that looks like this. So this is actually the X-ray CT scanned version of the barley that we were looking at. All right, so take this guy. And so here's what, I'm going to say what we did, but really Erica Mezquita is the brains behind this whole operation. So he's my soon-to-be graduated, almost former graduate student. He's very interested in the intersection of plant biology and TDA. So he did everything that you see is his work. So what he did was, so we get all of these X-ray CTs, and we have tons of panicles. So many of these different barley panicles that went through this machine. And so what he did was he actually, we decided that what we were going to look at was we were going to actually look at the seeds themselves. So we're going to study the shape of the seeds. So what he did was via image processing, he extracted out all of the seeds from all of these panicles. So this is very nice because it's a lot less labor intensive than how biologists would usually do this by literally taking them off. So he got something like 38,000 seeds. And so what he did was he built a bunch of sort of automated ways of coming up with the standard descriptors that biologists would use. So length, width, height, volume, I don't remember what else. So a bunch of just sort of standard traditional descriptors. And then on top of that, he did this Euler characteristic transform. So I showed you all these pictures with Euler characteristic transforms in 2D because I had 2D flat things. It turns out everything that I was doing is totally fine in 3D, where now you just kind of pick every direction, in this case on a sphere. So every direction on a sphere gets you a function, gets you an Euler characteristic curve, and that you can use that as sort of an input for your study. So in this case, we were just sort of testing out, let's just sample a whole bunch of directions. So in this case, he did something like 158 directions on his sphere. So each of these gets a vector and Euler characteristic curve. And he took that information and passed this into machine learning algorithms. So the results, let's see. Oh, I think this might be an old version of this slide. Oops. Okay. That's okay. I'm gonna send you all to the paper to get the actual numbers because I feel like we've got better versions later. So oops. But the main idea was that you can train a machine learning model on just your traditional descriptors. And the model that we were doing was, let's just work with the founding lines and tell me which founding line you actually came from, right? And so in this particular case, we were getting something like, okay, yeah, I apologize, these numbers are off. We got something like, at least for this slide, 50% accuracy using just the original traditional descriptors. When we tried to do the same thing but only use the topological descriptors, we also weren't doing particularly great, right? So again, according to this one, it's 40-something%. What was cool, though, was if you combine all these beasts together, you actually do considerably better when you combine the traditional and the topological data as sort of one giant long vector instead, right? So this is one of these things that I really think one of the things that TDA is particularly useful for is taking, in conjunction with sort of the standard things you might use, there's some additional information that you can sort of encode in your model that's using this shape and structure. Maybe it's not complete picture, right? These are lossy sorts of things, but at the same time, there's definitely something to be said for what's going on here. All right. I'm going to pause for just a second because I'm going to take a little bit of a left turn and talk about some sort of very different ways of taking input data into topological signatures and turning them into something that we can use for machine learning. And with the follow-up, please feel free to stop me at any point. I'm happy to answer questions. Get coffee first. I guess it's not morning for you guys, huh? Okay. All right, bit of a left turn. So we're going to talk about another sort of problem where you might want to do something related to quantifying and understanding shape. So what we're going to look at are dynamical systems. So in this case, we're going to look at underlying dynamical systems where you can mess around with some sort of parameter in your dynamical system and get different sorts of behavior. So the example I've got up here is everybody's favorite Lorentz equations. And if you pick very specific parameter values, you get things like the usual Lorentz butterfly, chaotic attractors, all that sort of stuff. But if you mess around with the values, you get all sorts of interesting behavior depending on your sort of setup. So what we were interested in doing was trying to measure and compare shape and structure in the resulting dynamical system attractor using purely data-driven methods, right? If you just hand me the underlying representation of your attractor, can I tell you things about chaotic versus periodic behavior and what sorts of things change accordingly? So a lot of the things we're going to do, we're going to compare to maximum Lyapunov exponent. So if you haven't seen this before, it's a value that you can attribute to a time series where or a dynamical system where you're trying to understand something about whether or how far apart 2 points that start really close together go from each other, right? So if you're living in chaos land, a little nudge in your starting initial conditions can make very, very large differences in your eventual locations. And so we're going to use this as our stand-in for deciding whether or not ground truth, we're actually looking at something that's periodic or chaotic. All right, so a lot of times we're also going to start with just a time series. And so one of the nice tricks that we have is that if you have some sort of input time series, we can try to figure out the underlying attractor of this thing by the following procedure. So what I'm going to do is I'm going to pick two numbers. I'm going to pick a dimension I'm interested in. In this case, I think my notation switches halfway. I think it's either M or N. I'm not sure. What I'm going to do is I'm going to decide on a dimension I'm going to embed in. So for the moment, I'm going to embed in dimension 3. And what I'm going to do is I'm going to look at 3 equally spaced points in my input value. And I'm going to compare that to 3 equally spaced points, or I'm going to use the 3 equally spaced function value points. So in this particular case, because I have T1, T2, T3, what I'm going to do is I'm going to actually look at the 3 points that are lined up with it, xi plus tau, and xi plus 2 tau. The equally spaced is the other part I get to make a decision about, right? So tau is sort of how far over am I interested in spacing these things. And it turns out that if you do a good job of picking dimension and that delay tau parameter, what I can do is I can treat these 3 numbers as just a point in a point cloud. So if these are xi plus tau, xi plus 2 tau, this thing is the point that's just got coordinates xi plus tau, xi plus 2 tau. So what we're going to do is mess around with this particular example and just slide this location along, and then you get a bunch of different points. So if I slide these points along this way, I get 3 different coordinates. And what ends up happening is that your point in your point cloud, in this particular example, just keeps following around in the circle. So what you end up seeing here is that periodicity in your time series turns into, well, periodicity this way turns into periodicity this way. And so we're going to measure this point cloud as a proxy for the original input time series. So the way that we're going to do this is with something called homology. Now, I'm going to apologize because usually if you're going to mess around with homology, you've had a full semester of a graduate level math course, and I'm assuming that not everybody here has had this, but bear with me, here's what this is. If you give me a topological space, I'm going to give you something that represents the underlying structure. And again, like the Euler characteristic, it should be invariant to topological deformations. Before, with Euler characteristic, it was very nice because my thing I handed you was a number. Now it is not so nice. Not that bad, though. Based on a bunch of assumptions I'm making, everything I'm going to hand you is a vector space. So I hand you a vector space. That thing should tell me something about my underlying structure. In this case, I actually hand you a series of vector spaces, each one telling me something about different dimensions. So in this case, homology, which is what we're building, in dimension whatever, homology 0 in dimension 0, this is essentially a vector space that tells me things about the number of connected components. So my vector spaces are always going to be Z2 because I like computers and 0, 1 is very nice. So in this case, I have a dimension 1 vector space, which tells me that I have a single connected component here. Fine, that's not particularly exciting, but I've got the same sorts of idea here where I have a dimension 1 vector space telling me that my donut, my torus, is actually one connected component. Where it gets fun is that you can do things with loops. So in the case of one-dimensional homology, which is this guy right here, what you can say is, all right, my circle here has a loop, and that is represented by the fact that I have dimension 1 vector space in one-dimensional homology, and that tells me there is one loop that goes around a circle. Again, not very exciting, but the fact that I can automatically do this is great. And this gets a little more fun when you start messing around with things like the torus. So with the case of the torus, that is a dimension 2 vector space. This thing has to do with the fact that, let's get a different color in here. There are sort of 2 loops that are going around this torus. There's the one that goes this way. There's the one that goes this way, right? And those 2, sort of any other loop you're interested in, you can build off of those pieces. And so what I'm doing is I'm basically saying this torus is more structurally interesting, at least in terms of loops, than the circle, and I can automatically come up with this vector space that tells me about it. Now, for computational reasons, I really don't want to deal with full generality topological spaces, so here's the actual representation we tend to have in a lot of our data. We work with simplicial complexes. So if you have run into abstract graphs, vertices and edges, this is basically that, but with higher dimensional stuff included. So we have a collection of vertices. We have a collection of simplices. Now in the lowest dimension of these things, they're just edges. And what these are just subsets of the vertices. So dimension 1 edges have 2 vertices involved, and they just tell me the endpoints of the edges. But then things like, I can do this in higher dimensions, so things like triangles. So a triangle is really just, I told you a list of 3 vertices, which encodes a triangle, and I promise you that the triangle is included in there. And I also have, I got a tetrahedron in this example too, so I have him down here, right? And so the additional requirement we're going to have is that this is closure of simplices. So if you have some sort of simplex, so say this particular triangle, I'm going to be required to have every sub-simplex included. So this edge, and this edge have to be included because that triangle was there. But what's nice about these is these are relatively, I'm not going to say simple, combinatorial structure that we can use as input to various data. And so what we can do, similar to the Euler characteristic idea, is we can look at filtering this beast, right? So as I change something about the simplicial complex, or as I start putting things in one at a time, how does the homology change? And so in this particular example, I can do things like watch the number of connected components. So here, I'm just going to put the number of things I can see rather than the full vector space information. But there are 2 connected components here. There's, there are 2 connected components here. There's 1 connected component here, and there's 1 connected component here, right? So what homology does in the background is encodes not only how many connected components you're seeing and how they change, but how they're related to each other. So in particular, I have 2 connected components here, and I have 2 connected components here, but the 2 here both end up in the same place on this guy, right? So those 2 vertices end up attached by the same edge, whereas this guy down here is a new one that just showed up. So what this does is it actually keeps track of that information. The fact that I had 2 connected components, but they merged into 1 in this case, 1 connected component here, although they kind of merged together into 1 giant connected component beast on this example, right? And so on. And so persistent homology is essentially, in the background, it's all linear algebra, but what's really going on is that we're trying to track where features that can be measured by homology appear and disappear in these sequences. So in this particular case, my 0-dimensional information, so 0 dimension here is currently marked with red dots. What I can see is that I had a connected component here that merged into somebody else over here. And what we do is we say that there is a birth at 1, and it dies entering 2. And so the way that we represent this information is by putting a dot in this thing called a persistence diagram, which says there's a connected component that showed up at 1 and merged into somebody else at 2. Likewise, in this example, I have this new connected component that showed up. It merged into the previously available connected component here. And so again, I have something that was born at 2 and died at 3, and that is represented by, again, a point in my persistence diagram. And in this particular example, I also have, so I also have infinite points. So this is kind of one of these weird anomalies. I have a connected component that showed up here. And since I'm kind of saying everything else had merged into it, it sort of lives forever. And that's represented by this weird little point that's, I'm going to kind of treat as being at infinity. This particular example, I'm just showing you things related to 0 dimensions. A lot of what we're going to actually be interested in are things like 1-dimensional stuff. So where do loops appear and disappear? So in this particular example, I have a loop that shows up here. Does the yellow show up? Yeah. I have a loop that shows up here and fills in over here. Now, I did not draw this in this diagram, but so this is a point in my persistence diagram representing 1-dimensional information that is born at 3 and dies at 4. And so what we do is we encode all this stuff in a persistence diagram and use that as input to whatever machine learning thing you want to do. All right, so how do I get from the point cloud embedding of all of these tokens things into something I can use with persistent homology? So for this, we're going to use something called the RIPS complex. So the idea is that if you have a bunch of points and you have distances between the points, what you can do is you can build a complex based on a fixed proximity parameter and try to see, basically add in edges as long as your distance between the 2 points is less than or equal to your proximity parameter. So in this case, my proximity parameter is going to be epsilon. And what we do is we mess around with the value of that thing. So the sort of connected, the diameter of these disks. As those expand, try to see what happens in terms of things merging up and filling in. So in this particular example, you're going to start, I'm going to actually draw one-dimensional persistence for this guy. So this is my one-dimensional persistence diagram down here. And what we're doing is we're looking for when loop structures appear and then when they fill in. So in particular, there's a loop somewhere around here that's born probably a little bit before 1, plus or minus. It continues along and then fills in somewhere before 2.2, right? So that thing is represented by the fact that I've got a point in my persistence diagram that's a little bit less than 1 and a little bit after 2, right? Similarly, I have the overarching large structure. Let me get a different color. That's green going to show up. I've got the overarching large structure. So this big circle here, that thing shows up, okay, plus or minus 1.8-ish. But it fills in, well, sometime between, this is a nonlinear set of pictures, sometime between 3 and 6, right? By the time I've gotten here, that loop structure is definitely filled in. And so again, I have a point in my persistence diagram that is, let's see, born a little bit before 2, dies a little bit after 4, apparently. Right? So what we can do is we can use these persistence diagrams as input to our machine learning algorithms to sort of see what we can represent in terms of what's going on. For the sake of time, I'm not going to go into this too much, but we do have available metrics to compare these diagrams. So I said at the beginning that we wanted to be able to talk about comparing two topological signatures and promising things about whether or not you have close to the right answer in terms of your representation. It turns out that the answer is yes. We have these metrics. We have theorems that say that you can do that. Again, if you want longer discussions later, I'm happy to expand on this general idea. Let's get to what we're going to do with these things. What we're going to do with these things is, again, I want to find a way to turn this into something I can hand to machine learning. And in order to do that, I need to be able to turn it into something that looks like a vector. And the goal with all of these things, and the reason why this is difficult, is that you want to be able to turn it into a vector that somehow preserves the original input structure. So in particular, these things are a list of points, but the sorted order of the points shouldn't matter. So I don't want to just hand the pairs of persistence points, the birth, comma, death times of all of my things, because that's losing something about the underlying structure. At this point, there's now a wealth of options for things to do if you have a bunch of persistence diagrams and how you can actually represent these. Some of the most commonly ones used are what are called persistence landscapes, where the idea is that you build a series of functions, vectorize those functions, and use that as your representation. There are persistence images where you essentially treat this thing as a heat map in terms of locations where you see the most persistence points. This is particularly helpful because in a lot of applications, you can have very, very dense persistence diagrams. And so this vectorization is particularly useful for that. There's a version that we had developed called template functions, where the idea is to essentially probe different locations of your persistence diagram space. Again, all of these have the result that I have now a vectorization of whatever my input persistence diagram was. And now if you have 300 input diagrams, that turns into 300 vector point representations. And again, you can pass this to your favorite machine learning algorithm. Let me show you some examples where we had actually done this. Right, okay, so here's an example going back to this dynamical systems thing, where what we're going to do is we're going to mess around with, in this case, the example is on the Rossler system. So what we did was we built a supervised learning problem where I had some sort of parameter value I can change in my dynamical system. I have the maximum Lyapunov exponent, so that guy is here, which tells me something about whether or not the time series I'm evaluating is actually periodic or chaotic. And what I can do is I can then take some subsample and train a model based on just these persistence vectorization representations of those time series. So what we did was we then tried to classify everybody as being periodic or chaotic. And what ended up happening was so in this particular picture, so the pink regions are the values of my alpha parameter for which I am actually supposed to be periodic. And my predictions are correct with the errors, the misclassifications happening basically right on boundaries, which is to be expected. So anything that's getting kind of close to changing from periodic to chaotic is where the model starts getting confused. But in general, this is a very nice and automated way of building some sort of representation. Again, this was a bit of a test proof of concept as opposed to something we really want to, do in practice. Now, I'm going to run out of time. Let's see. What do I want to go from here? Okay, so let me try to talk about one more thing, and then y'all can cut me off. So the trade-offs of this are basically that persistent homology is pretty computationally difficult. By that, I mean we have better and better software to do things, but we're sort of running into bottlenecks related to the algorithms just can't be improved. So what we've been doing more recently is trying to find smaller representations of my starting input data and using that to pass into whatever your machine learning model is. So one of the things we've used most recently is something called an ordinal partition network. So this is a very similar idea to this tokens embedding framework. But instead of encoding the values of the 3 numbers that are on the time series, I'm going to encode the order of the 3 numbers in the time series. So in this case, I have a permutation of, again, in this case, 3 numbers. And so every stopping point I'm interested in gives me a permutation of 3 numbers. And I'm going to treat that thing as a graph. So anytime I get to a representation where I have, say, the 6th permutation in whatever order I've handed to you, if I shift my numbers along a little bit, turns out that what happens is that goes from that to being, say, the 4th permutation in my list. And then it goes to the next one, and then it goes to the next one, and then it goes to the next one. And what I can do is I can keep track of which permutations are visited and build this graph off of it. And the graph is something that I can actually measure with things like persistent homology. So there's a similar idea to this setup with the RIPS complex and the point cloud, where I actually come up with distances related to distances between the nodes based on proximity from who actually got visited in this ordinal partition network. And again, the result is I start with a graph. In this case, I'm actually filtering this full simplicial complex, and my output is a persistence diagram, which hopefully represents something about the underlying structure. In this case, I have 2 points in my persistence diagram, which has something to do with the fact that I have 2 loops in my underlying graph. All right. Point being, though, if I'm going to ignore that. Let me find the results right. Then if I can start trying to predict which sorts of systems I have, can I measure things related to the persistence diagram to say whether they are periodic or chaotic and whether or not they're sort of related quantities. So again, this is the maximal Lyapunov exponent is here. We use some rather simple vectorizations of my persistence diagram to try to see if we could separate things. And again, the idea is that if you have less noise, this actually does particularly well in terms of separating the different sorts of behaviors. The more noise you have, nobody's going to do well, so that's okay. All right. For the sake of time, let me just get to some summary stuff. So what's the point? So the whole idea here, and I think what I find to be the most difficult version of anything that we work with, is trying to figure out how to encode something about your starting input data as something that you can represent as some sort of topological signature. Finding ways to build, in particular, filtrations, these sequences of simplicial complexes or images or other sorts of one parameter slowly changing version of your space. Once you have that, there's a lot of methods that are available for turning that into some sort of topological signature. And then once you have a topological signature, there's a lot of methods for turning that into something that you can actually use for analysis. The game is oftentimes finding a filtration, finding a representation that actually encodes something about your data that's going to be useful. So for the sake of that, I'm happy to take more questions. The work that I showed, so Erica Mezquita is the PhD student who did the large amount of the barley work. The work that I showed was with the time series was largely with Faraz Kasawane and some of his and my students. And so for that, thank you all for your attention, and I'm happy to take questions.
Okay, so thank you for your very interesting and also visually appealing talk. For this way of somehow introducing some basics of topological data analysis through examples and applications. So now it's time for questions and comments. So if anyone from the audience wants to have the first go, you can raise your hand, use the chat, or use the question and answers option. But as it is a tradition, it's usually me who throws the first question while people. So yeah, first a curiosity. I wanted to start. You are talking about topological signatures. So yeah, if you look somehow, I checked it on my phone while you were talking. Like what happens when you look for this term in Wikipedia? Somehow the signature in topology is something very, like, people talked about that in a very concrete way, some signature of some quadratic form. So I wanted to tell you, like, this way of referring to these objects. Is it something very recent? Is it that you know something about the story? Do you know somehow what makes something a topological signature?
That's a good question.
In your sense?
I think, I'm trying to remember where this started. I think my plant bio collaborator started using the term. And this was largely to try to explain things to biologists in a way that could kind of get across the sense of the fact that we were losing information, but encoding hopefully something useful. So yeah, so I think this might be a me term. I'm not sure.
Okay.
That's a great question.
So,
I should go. I hadn't thought about that. I should go Google that.
Yeah, and when you were talking about the barley case and you were doing these three cases, traditional, topological, and then combined, the topological, there was the ECT, but there was also the KPCA, I guess, the principal component analysis.
Yes.
I wonder if you could tell us a bit about that.
Yep. You can So what ended up happening? Okay, so we have our traditional descriptors. We had 11 of them. This is a sort of reasonable vector to work with, and the machine learning was happy. The Euler characteristic version, the giant thing I'm sweeping under the rug is the fact that I have 158 directions. I have, I didn't write down how many, something like 40 stopping thresholds. So each direction gets me 40 different numbers. 40 times 158 is bigger than I can think about right now. And so passing that into your machine learning algorithm was getting us basically garbage. So what we ended up doing was taking the full Euler characteristic representation for all of the barley seeds and using lower dimensional embedding to try to get something that was way more reasonable. So in this case, and again, this is older version of the slides. The version in the paper uses UMAP, I think, but we're still going order of magnitude around 10 or 12 dimensions. And so mapping pretty heavily down to lower dimensions did a lot better in terms of both computation time for the machine learning algorithm, but also results in terms of our classification accuracy. Yeah, so that's why we ended up with 12 descriptors instead of 158 times 40.
Okay. So my question was also about, like, if you could tell a bit about KPCA, this kernel principal component analysis.
That part. Yes. Yeah. So what we ended up doing in this case, we had, okay, so the actual model that we were building, what we had, so those results were just talking about the original founders. So we have results that are applied to the sort of later stuff with sort of predictive modeling and trying to say what you think, how much of the founders sort of made it through the lines. But in this case, what we were doing was we were actually measuring if you have original labels based on this barley panicle came from this particular founder, then what we were doing was we were trying to figure out, predict which of these founders you were actually working with, right? So In this case, I think he just did 1 against all for each of the different labels and built a predictor that way. Does that answer your question?
Okay. Yeah. Well, I was wondering if as you did with other concepts, you could tell about like the principal component analysis very briefly.
Oh, well. like what PCA is?
Yes,
okay.
like very the way you did with other concepts. That was, I think it's very nice to have like global view to say like yeah, this term essentially means this. Yeah, this is what.
Yes, I guess we're going, and let's see. I'm not going to remember how all the kernel PCA stuff works on the spot. The idea with PCA is you want to take higher dimensional descriptors and try to come up with some linear combination that gets you a lower dimensional version of it. And so in our, wait, do I have, bad idea. I might be able to pull up pictures that will make me remember this better. What we were doing was we were looking at linear combinations of different, the different representations for these directions, and then trying to come up with lower dimensional descriptors that were combinations of those. Now, the perk is that if you're working with lower dimensional versions of these collections of the initial inputs, you can actually pull that back to figuring out which collections of directions were actually useful, right? So in this case, these different descriptors will be something like some linear combination of, I don't know, hopefully maybe they're nearby each other, but a bunch of different directions, right? Where your actual descriptor is now a linear combination of just the vectors in that particular direction, right? Now, the nice part is if you can go backwards, for this particular example, we spent a bunch of time trying to figure out which of the directions were actually getting used. In this example, because these barley seeds kind of look like a thumbprint, the directions that the machine learning algorithm were pulling out were exactly the ones that you would think had the most in terms of variance in the underlying system. So the directions that were perpendicular to where the thumbprint were and perpendicular to the long way, I think, are the ones that show up the most, but I don't think I have that slide in here.
Okay, thanks. That's interesting. Yeah. Did you, by the way, are you planning to apply this to other grain? Or like, is there any other case where you could have a similar database, or there is not?
Yeah.
This is the very
So we're doing this on a bunch of stuff. So right now, the most recent one, which I don't have pictures of, but the one we've been playing with the most recently is this this walnut structure. So the thing with the barley seeds, the barleys are relatively simple, you know, for better or for worse. The seeds are all just sort of like a football with a little dent in them. What's fun here is that the insides of these walnuts are sort of, they kind of look like little brains. And so you can do the same thing with this little brain structure and try to use these as representations. So the other thing that's really nice, well, so the example that I showed you with this application with the barley seeds, a lot of what I said was reliant on shape alignment. So it relied on the fact that we were able to take all these barley seeds and relatively easily align them with each other. So that the thumbprints were all going the same direction, the football shape was going the same direction. Sorry, American football shape was going the same direction. In this particular case, it's a lot harder to do that. And so we're working on sort of modifying the model so that it's a bit more translation invariant, so that if I can use this Euler characteristic transform and get you a representation of my underlying data, but I don't want to have to align all of these different walnuts, right? And can you sort of deal with that accordingly?
Okay, so after breaking the ice, I guess also melting it and almost boiling it. I don't know if there's any question from the audience. Yes, Carlos, please.
Thank you very much for the nice talk. How do you use TDA with weighted graphs?
Excellent, perfect. I got like 30 slides on that. Look out. Okay, so it is non-trivial if you have, okay, so there's a trivial version and a non-trivial version. Let me show you what ended up happening with these guys down here. So in particular, so this is going back to that ordinal partition network idea where we had some sort of noise in the system, and noise in the system could create these obnoxious shortcuts. And so what I didn't say was that earlier, everything I was looking at, I just ignored weight entirely. So all I had was, here's a graph, go measure it. Putting the weight information back in turned out to be much more tedious than I was hoping. But the following sort of things generally worked. So in this case, so this is the same sort of ordinal partition network, and in this case, one of them has a sort of very low weight. Is that showing up? There it goes. A very low weight edge added in the middle. So the one weird thing with ours was that a lot of the systems are built so that you are doing sub-level sets. So what I'm actually doing is I'm building up a filtration, and I'm watching how the structure changes as I increase this parameter. The problem here was the fact that I want to have everything with a high weight first, and I want to decrease the parameter. And so you have to pick how exactly you're going to turn your decreasing function into an increasing function. In our case, you could just increase based on doing something related to just the shortest weighted path, which is already a little bit wonky. We had the best for this particular example, so there's no one right way. For this particular application, we did the best related to looking at diffusion distance. So we took the weights on the edges. We treated this as some sort of probability measure, right, where your probability of going from one place to the other is higher on the higher weighted stuff. And then we did a diffusion distance construction from one vertex to the other. And so that ended up essentially keeping track of all of the higher weight overarching circles that we were looking for the best, as opposed to some of the other options that we messed around with in this paper. And so I'll give you, where's my paper? That's, there's an archive number for that paper too, if that's helpful.
Excellent, thank you.
Yeah.
Thank you very much.
Okay, any other questions from the audience? While you think about it, I have another one from about the second part of the talk. On slides 28 and 29, you just somehow mentioned very briefly this metric that you actually also mentioned at the very beginning when you said it should be comparable, and then you compare with a metric. I wonder if you could just give some more information without necessarily going into the details.
Yeah. So here's the sort of general philosophy. If I have a starting input shape, so for instance, if I have, do I have a good example that's back here? Not really. Okay, let me draw a nice example. Hold on. There we go. Okay, so let's say I'm interested in some sort of shape, and in particular, this game is very good at finding circles, right? So maybe this is data point cloud 1. Oh, I shouldn't use chi, we're using that for other things. X1, and maybe I have another one that's maybe got a little bit of wonkiness to it, and maybe there's some other small things, and maybe that's X2, right? So the idea here is that the overarching structure of your point cloud should be, okay, we should have some sort of, well, maybe not quite so big circle, and maybe some noisy things that are happening on the bottom, and maybe this guy is a bit bigger, and maybe there's some other noisy things that are down on the bottom, right? The big philosophy here is just the fact that if you have a large circular structure that lasts for a long time, birth and death are far apart from each other, and so you end up, pardon me, with points that are further from the diagonal. So first off, I want to have some sort of measurement that tells me that these persistence diagrams are similar to something where you have the high persistence points and generally treats these things as being noise. So those points should be almost the same thing as being entirely on the diagonal and not there at all. And then on top of that, I should be able to compare these sorts of constructions based on the fact that I've got a high persistence point here and a high persistence point here, and how similar are those. So what we do is we work with this idea of matchings, where so I have two persistence diagrams. So I have my oversimplified example over here on the left. So again, this is the birth time and this is the death time. And what we do is we come up with a matching between the two overlaid persistence diagrams that tells me essentially how far off they are from each other, right? So in the drawing I have here, I've matched up the square points with the purple circles in a way that sort of makes them matched with close things as much as possible, but with this weird caveat that I'm allowed to match things to the diagonal. So the idea here is that things that are far from the diagonal should be probably generally matched together, otherwise your distance is going to be large. But if you're close to the diagonal, you're almost the same thing as not being there at all. And so what we can do is we can measure distance based on the minimum cost of this matching, where cost is defined as how far apart any 2 points in the matching are, right? And so the reason this is nice is if you give me 2 starting point clouds that are very similar, similar here being measured in, say, Hausdorff distance, what I can promise you is that the distance between the diagrams, so this is called the bottleneck distance between these 2 diagrams, is upper bounded by your original distance. And so what's useful here is that if you have a point cloud and maybe its noisy cousin, the diagram you can't have from the actual underlying correct answer is very similar to the diagram you would have gotten if you were or the diagram you got from your noisy version. And so we spend a lot of time when we're building these vectorizations and things like that, trying to make sure that any sort of vector representation also preserves these sorts of properties, right? So if you give me 2 persistence diagrams and I'm going to turn them into some sort of vector representation that I'm going to hand to your machine learning algorithm, I really want to make sure that the vector representations are also very close to each other, so that the machine learning algorithm isn't also taking similar diagrams that have similar structure and putting them on opposite sides of whatever planet you're measuring.
Okay, when you define the cost function of the matching, you have this maximum. What happens, for instance, I'm wondering if you take can you do something like L2 here? Yeah. So what happens then if you go for L2?
Yeah. So this is bottleneck. If you swap this out for some sort of LP looking thing, you get, okay, we stole this term. You get the Wasserstein distance.
Okay, and does it behave equally nice? There is a theorem, like, is there, I guess there are also perhaps some inequalities between them, the LPs and so on? Okay.
Yeah, you get a lot of, there are versions of this theorem that are very similar. You have to make some additional assumptions on your input data. In particular, these tend to be the version I'm thinking of right now, you tend to do it in terms of like sub-level sets of functions, then you have to require those things to be Lipschitz. You have to have something a bit nicer. The idea being that if you have this Wasserstein version, rather than measuring the maximum difference of anything, it's a summative version of everybody's matching everywhere. So if you have a lot of noise, the Wasserstein distance, the LP version, will actually pick up all the noisy bits, whereas the bottleneck distance won't. It's just easier to state. Okay. But in practice, I think that's probably the thing that gets used much more often, just because it's much more discriminative, has a lot more information in terms of comparing these things. So actually, one of the things you can do, rather than vectorizing, if you have a lot of persistence diagrams, we can do things like treat these things as their own data points, come up with pairwise distances, and look at things like MDS projections of whatever your distance measure is, right? And so we've done a lot of things related to, like, yeah, can you get lower dimensional embeddings and things that can sort of really keep track of the structure of your original metric space, where you're thinking about these diagrams as living in this metric space. And then passing this through, yeah, clustering and whatever else after you've done your MDS.
Okay, thanks. Still have time for one more question, at least, if someone wants to have a go. I still have one. Yeah, it's more of it's just relaxing now. So I asked you about this metric also because somehow you work on topological data analysis, right? But this notion of metric could be considered also going to the geometric side, right? Yeah. So what's your viewpoint on somehow, say, topological data analysis and to what could be like somehow geometric data analysis? Because I know it started all as topological data analysis, and now somehow geometric data analysis started to come out later. So what's your take on this?
I think that was a failed opportunity, and the name probably should have both in it, but we've kind of, there are a lot of people who actually call what, you know, this sort of field of research generally GTDA or some sort of geometric stuff. In particular, things like this example I just showed you. So there's the sort of top level version where we're taking all this topological representation and we're doing things related to topological representations that completely ignore anything about the underlying geometry. But because we're applying them to embedded data where the geometry is somehow still incorporated and the filtrations we use are still incorporated with something about this geometric embedding shape size information, a lot of the tools that we use actually are measuring both topology and something about the geometry at the same time, right? So in particular, if you ask a topologist, right, a circle that has diameter 1 and a circle that has diameter 300 should be the same. But if you measure it with a lot of these tools out of the box, those two will show up with very different persistence diagrams because one of them has a circle that lives longer in whatever filtration you build, right? And so a lot of the things that we're doing are actually encoding things about the geometry, but using tools from topology, if that helps.
Okay, yeah, thanks. Okay, so if there are no more questions, yeah, let me take this last opportunity to thank you again. Thanks a lot for finding the time to share with us your knowledge and to also your time to answer, sorry, all our questions. And just let me remind the audience that in a month, on the 26th of April, we'll close this year's cycle of Colloquium, actually with Jürgen Jost, who will tell us actually about this side of geometric data analysis. So you are all welcome to join us, and hope to see you then. Okay. Thanks a lot to everyone. Bye.
Thank you.
Thank you.